Hello, this is Jack Jackson. In this video, we're going to be introducing spherical geometry. So we're in the process of introducing Euclidean geometry, taxicab geometry, spherical geometry, and hyperbolic geometry in this series of 4 videos. And we're going to introduce these non-Euclidean geometries along with Euclidean geometry to show that we have multiple ways of looking at geometries, and also to show that we can look at these different environments and develop geometric ideas in parallel. Okay, so in some applications, Euclidean geometry makes the most sense, such as when moving around a flat surface, such as a tabletop. In other situations, taxicab geometry makes more sense, such as walking around Manhattan. In still other situations, spherical geometry is the most practical. After all, we actually live on the surface of, or at least approximately, a sphere, rather than on a flat Euclidean plane. So measuring distances and finding shortest paths on the surface of the Earth makes more sense in spherical geometry. And this motivates the model of a plane in spherical geometry. In spherical geometry, a spherical plane is a Euclidean sphere of a fixed radius. We'll take the Euclidean radius of the Euclidean sphere, the spherical plane, as being one unit, one spherical unit. This way, the Euclidean arc lengths along the sphere are exactly the same as the lengths in the plane in spherical geometry. So the first question might be, what would be a path of shortest distance? In other words, a line segment. What would that look like in spherical geometry? So to investigate this, we will use a physical manipulative kit called Lennert spheres. And here's a picture of it, of a Lennert sphere kit. And in this kit, the sphere is considered a plane in spherical geometry. The radius of the sphere as a Euclidean geometric figure is 1 unit in length. And the kit comes with some construction tools analogous to basic Euclidean drawing and measuring tools. It includes spherical versions of a straight edge, a ruler, a compass, and a protractor. So here's basically what comes in the box. This right here is the plane, the spherical plane, which is, of course, a Euclidean sphere, but it's a plane in spherical geometry. This thing right here is just a stand to hold it. It's in the shape of a Euclidean torus, like a donut or an inner tube. And this little, let's see, these little transparencies can fit over that to draw things. They're half planes in spherical geometry, or hemispheres in Euclidean geometry. Let's see, this object right down here at the bottom is a spherical version of a compass. Like a compass, you have a pointed part and a part that draws. To draw, you insert a transparency marker. So this should be not a permanent marker for sure, but actually a wet erase marker, like a transparency marker. If you're in my class, you should have gotten some in there. There are different little adapters that you can plug in there for different size pins. The blue one works for the pins that I actually have in the box. And they may start to run dry. You may need to actually buy some of those transparency markers to put in there. Be sure you not use permanent markers, or you're going to be buying me a new Lennert sphere kit, and they're not super cheap. They're not real expensive though either, considering how much good we're going to get out of them. So anyway, you place this there's this little rubber piece like this that you mark a point on the surface of the sphere, and you put that there. You put this pointed in the center of that, and then you twirl it around this thing here, and the marker will trace out a path, which is a fixed distance, and that's a spherical circle. There's one right there in red. Okay, when you be careful when you're drawing on this, you're going to get your hands all colored up. You might want to get some like little food service gloves to hold on to this while you're working it. It seems like no matter how careful I am, I always end up with my hands colored up. But anyway, when you're done with this, you can just wipe it off with with a wet paper towel, just with water. You don't need to use any special chemicals, just with a wet towel, then dry it off with a dry paper towel, and you should have a clean sphere if you need it. Let's see what else. Okay, so we can draw with this thing right here. This is actually my straight edge and ruler. So you have to be a little careful about this. This thing needs to fit snug over the sphere. And then this outer edge along here, the bottom part, be sure you're not using the part around here or here, but the outer edge is a straight edge in the sense that it's drawing a spherical line or line segments. And so it does have marks on it so they can be measured as well as measuring their length. We can use that. Now there's also one of these cross ones. I can't tell from the picture if it's right here or right here, but one of these has marks on it. That's also part of a spherical line. You could use that to draw, and it's actually perpendicular to the one down here. So we can use that to draw what you could do with the straight edge. Connect 2 points up to make them into a line segment. Construct a line segment. That's basically what a straight edge is for. And you can also use the markings on it to measure. If you make two rays, that makes an angle if they have the same endpoint, and you can take this right here and measure the angle, and that's called a protractor. And this fits over that. The center of that's going to be at the vertex of the angle, and then the markings on here are going to allow you to measure that. It has a little book that comes with it, and then these little things can be pushed inside of here with a transparency over them to basically turn this into a globe you can write on. I think I have removed those from the sphere kits that we have at our school that I have checked out to my students. So here's a task you can try. Put using a transparency marker, mark 2 points on the Leonard sphere, and take a string. So go find you a little piece of string. There might be one in your box already. If there's not, go ahead and get some string, and if you don't mind, just leave some of it in the box for the next person. But get a little piece of string and hold it at one of the 2 points. Put your finger on it and hold it. Pull it tight, pull it taut, and make it go to the other point. Okay, keeping the string along the surface of the sphere. That path is going to be a path of shortest distance, so that makes it a line segment, a spherical line segment. It's not a Euclidean line segment, but a spherical line segment. The Euclidean line segment would have to go into the interior of the sphere, which is not part of the spherical plane. Okay, so what shape is it? If we were to continue this out to a, just extend it on and on and on, continuing around, what shape do we result if we extend it as far as possible? What would that shape be called as a spherical object, and what Euclidean shape is it? Okay, now of course we could do this on any spherical shape, say the Earth, globe. So doing this on a globe shows the shortest path between 2 points, such as the minimal flight path between, say, San Francisco and Tokyo. So here's a kind of a crude spherical globe, blow-up one. And I found Tokyo here to San Francisco here, pulled the string tight, and that path is the shortest path. Not down around this way, for example, or not up this way. That's right there. That's the shortest path. Certainly not around this way. That'd be way too long. So that's the shortest path there. Okay, so here's, see if you can, I'd like you to actually get your sphere out if you've got one of these things, or if you've got a globe, you could do the same sort of thing, and see if you can answer these questions here before we go any further. It's going to be important for you to think about this really before I even give you the answer. So the question is, if we continue this process of taking the shortest one and maybe continuing this on in a sort of a longer and further points apart, what shape would we end up generating? In other words, if we extend a line segment, what do we get? well, we get a line, right? If we extend it as far as we can in both directions. So it's a spherical line, but what Euclidean shape is it? See if you can kind of figure that out yourself. And then when you've experimented with this a little, come back to this video. But I'd like you to do that yourself now. Press pause now. Okay, so now hopefully you have gone and actually experimented with this yourself, and you've come to some conclusions. What you should have found is that extending out these line segments to make longer and longer line segments, extending all the way around the sphere, results in what would be a spherical line. But what it is, Euclidean geometry, it's what we call a Euclidean great circle. That is a Euclidean circle centered at the center of the sphere as a Euclidean object, right? With a radius equal to one spherical unit, the radius of the sphere. Another way to see the spherical line, Euclidean great circle, is take an intersection of the sphere with a Euclidean plane containing the center of the sphere. And where those intersect will be a Euclidean great circle. Can you think of an example of a Euclidean great circle on the Earth? Think about that a minute. What would be an example of a Euclidean great circle on the Earth? If you need to think about it a minute, press pause. Well, did you come up with the equator? Yeah, the equator is a good example of that. Another one is any of these longitude lines. They go from the North Pole to the South Pole, and if you go all the way around the Earth, extend them out, okay, that is going to be a Euclidean great circle or a spherical line. So if we take any longitude line on Earth going from the North Pole to the South Pole, then it's half of a spherical line, so that'll be a spherical ray. And if we continue a longitude line all the way around the Earth, we get a spherical line to the North and South Poles. The equator is another example of a spherical line. However, be careful. These latitude lines going around like this that are marked are not circles except for the equator. They are circles, they're spherical circles and Euclidean circles, but they're not spherical lines unless it's the equator. So if you want to go the shortest distance, well, look here. These are kind of close to the same latitude. Okay, if you were to go, so Tokyo then is, say, due west of San Francisco, you could follow this latitude line, right, and stay going east all the time. But that's not the shortest path. The shortest path is up here. So here's another example down here. New York and Madrid are pretty much at the same latitude line. So here's New York over here, and here's Madrid here. So Madrid is due east of New York. If we were to go along the same latitude line, which would be just above this one that's marked in here, and we would follow that around here, we would be going due east the whole time. But that's a much longer path than we go the shortest path, which is along this is a spherical line segment here, which is from here to here. Same way if we go from New York to Paris, go on a little past Madrid on to Paris. Paris is a little bit further north than New York, but same basic idea. If we go mostly just going east and just a little bit north, we go along this path, but the faster path, shorter path is this way right here, which is quite a bit longer. So here's a task for you, and it's important that you actually do these tasks yourselves. There's no substitute really on spherical geometry for actually getting an actual sphere out and actually trying some of this stuff. So on your Leonard sphere kit, mark 2 points with your little transparency marker, and get the straight edge or ruler tool to make the line segment with these 2 points as endpoints. And you maybe check that with your string. Okay. So also construct 2 more points and then construct a full line. So here's a question for you. Is it still true that 2 points determine a line? Remember what that means? Can you say what 2 points determine a line means? Remember, that means that given any 2 points, there exists exactly one line containing them. There always exists a line containing them, and at least one, and there always exists at most one. So exactly one line. Is that true in spherical geometry? Just kind of investigate that. We'll come back to that idea in a bit. Okay? Press pause, and when you've investigated this, come on back and we'll finish this video. Press pause now. All right. We can also look at this particular activity here. This one is authored by Tim Brzezinski. He's a GeoGebra whiz and it's got some really good GeoGebra activities for all kinds of things, including geometry. And so we could look at that. So let's see if I can get it to open up here. Okay, I think I'm getting it to load up over here. Okay, so this is his activity here. And so he's saying some of the same things that we've said here. And here's the activity. Here's a sphere using the 3D capabilities of GeoGebra. And I can move this around. I can change the sphere radius here. I can change how the shading is with this. So I can make it where I can't even see through it at all, or to where I can see through to the other side of the sphere. So you make it sort of somewhat transparent so we can see what's happening on the other side. So let's look at what happens here. So if we want to go from one point to the other, okay, so here's 2 points here. Let's see what's happening here. So he's taking this out, and this is a distance. Straightening that out and make it straight. And then we notice that which one is shorter. The pink one is shorter than the yellow one. So the yellow one, for example, might be going along so any path that's longer. The pink one is actually along the line. It's actually the shortest path. So this right here, going all the way around, is a spherical line, and the pink is a spherical line segment. Here's some other path going from here to here. Perhaps looks like it's a circular path with the, say, center of the circle, so right about in here somewhere. And we got that. So again, we're talking about the lengths on here are actually the same as Euclidean lengths. Take that path, that's string or wire or what it is, wherever it is, straighten it out and just measure it with the Euclidean ruler, and that's the distance, and we can see that the pink is definitely shorter than the orange or yellow. Okay, so that's that. Okay. Now, it turns out that you can actually develop a dynamic visual virtual environment for GeoGebra, kind of like what we were just in, for exploring spherical geometry. Heather Price is another math educator who's created something like this, and she created an environment I opened up, I found there were a few things that weren't really working exactly as I wanted them to, so I did some tweaks to it and created this particular activity here, which you have a link to. Notice that the normal GeoGebra tools have been replaced with new tools that are equivalent. We can still do points, but what can we do? We can create a point there on the surface, and once again they're dynamic. There's some coordinates of it. If I have a point and click on it, it creates its antipodal point, which is on the other. That's completely on the other side of the surface there. You can kind of see where it is. So this is on the back side here. You can take and make a spherical line through 2 points, and we can see that going all the way around. That's our great circle, when we would call it in Euclidean geometry. And we can make line segments, a spherical segment or a line segment. You have to have the points first on this one, so I need to make 2 points, and once I have the 2 points, I can click on the 2 points and it makes a line segment. So that's a spherical line segment. Let's see, what else can we do? We can talk about perpendiculars, we can construct angle bisectors, we can construct a ray. Again, let's make 2 points, and we construct a ray through there. The first one's going to be the end point, and then the other one, and that's it. It's going to be half of a line, so it's going to go from one point all the way around to the antipodal point. Okay, we can measure angles, create circles. Here's a spherical circle. Let's see, circle by, I think this is about 2 points. So let's see, the spherical circle, we should be able to go from here to here. Yeah, that makes a circle. The first one was the center. The second one is a point on the circle. Okay, we can make different things. We can still do some of our normal things like adding some text. We can rotate things around and do some things there, add sliders, check boxes. Here's kind of a list of a lot of the tools. So notice these are actually custom tools that were created to use with this environment. So we'll be able to investigate some things in this environment, and you have a link to it in the notes that we just did, or you can see it right here. There's the version that I worked on based on Heather Price's earlier work. So here are some more questions for you. Remember that we're letting the Euclidean radius of the sphere to be one spherical unit. How long is a line? Is it infinitely long, like the lines are in Euclidean and taxicab geometry? Are all spherical lines the same length? Do they have a finite length or not? So that's an interesting question. Okay, so think about that a minute. Come back when you've thought that over a bit. Press pause now. Okay, just hold those questions for a minute. Let's keep going here. If we construct a Euclidean line through a point on the sphere, and the Euclidean we construct a Euclidean line through a point on the sphere and the Euclidean center of the sphere, then it will intersect the sphere in exactly one other point on the exact opposite side of the sphere from the original point. These points will be as far apart as possible on the sphere. How far apart are they? Again, another question I want you to think about. These 2 points are called antipodal points or polar opposite points. every point A in the spherical geometry has exactly one antipodal point that we'll notate as A prime. All right, so let's think about the answers to these questions. Unlike in Euclidean and taxicab geometries, in spherical geometry, lines are not infinitely long. All lines are as long as the Euclidean circumference of the circle, which is 2 pi r. Since we take the Euclidean radius of the sphere, spherical plane, as one spherical unit, r1, all lines have length 2 pi. Antipodal points are pi spherical units apart. So the maximum distance from one point to another in spherical geometry is pi spherical units. So for example, let me go ahead and type this in here. The longest between 2 points on Earth is the distance from the North Pole to the South Pole, which is pi times the radius of the Earth. So the distance metric has an upper bound. Of course, it always has a lower bound of 0 for any metrics, but it has an upper bound to it. In spherical geometry, all distances are in the interval from 0 to pi. All right, so here's another task to investigate on the Leonard sphere and in the GeoGebra activity. So try this on both. What do you notice when you construct any two lines? So just pick any, make a line, make another line, do it both in GeoGebra in that activity that I just had for you, and then also in the Leonard sphere. Okay, what do you know? What does this say about parallel lines in spherical geometry? And how many lines go through a pair of antipodal points? How many lines go through a pair of points which are not antipodal? So think about that for a bit. Try it out yourself. It's important you try it out yourself. Then come back and then let's see what happens with that. Press pause now. Well, I don't have my Leonard sphere here, but hopefully you've tried this out yourself. Let's take a look back at the at this here. So let me just kind of delete a few things. Let's see here. Okay, so let's kind of go back to the beginning. So there's a couple of pairs of points, and let's just make a line. Yeah, spherical line. So take these 2 points and make a line, and these 2 points and make a line. Well, look what happens here. They intersect right here, but they also intersect on the opposite side. So let's calculate the intersection of that line and that line. And there's 2 points, E and what's called D here, but it's actually E prime, or when D and E are antipodal from each other, right? And if we move around our original lines, they always intersect in 2 points that are polar opposites. And let me show you something else. If I were to create a line going through, say, that pole and that one, it always goes through the other pole. So no matter where I put this, notice that there are infinitely many lines going through that antipodal pair. So 2 points do not determine a line, right? If the points are an antipodal pair, there are actually more than one line, actually infinitely many lines, through those 2 points. So remember, 2 points determine a line means there has to be exactly one line. Okay, so we get a weaker version, a couple of weaker versions. One is, given any 2 points, there's at least one line containing the 2. It's weaker than we have in Euclidean and taxicab and hyperbolic geometry. Now it is, if we can put the restriction, if the 2 points are not an antipodal pair, then there's only one line through them. So that's why we were able to do this construction here. I picked 2 points that are not an antipodal pair, and it worked out. So that leads us to some interesting differences about spherical geometry than the other 3 geometries that we're going to look at. So some answers here are, when we construct any 2 spherical lines in the same plane, they must intersect in exactly 2 points, an antipodal pair of points. So there are no parallel lines in spherical geometry, no such thing. Furthermore, there are infinitely many lines through a pair of antipodal points. Okay. So, for example, there are infinitely many longitude lines through the north and south poles. 2 points do not always determine a line. However, if the 2 points are not an antipodal pair, then the 2 points do determine a unique line. So these observations show that that the spherical geometry does not obey our entire set of postulates that we have so far for unified geometry. Well, we want unified geometry to include spherical geometry, so we have to fix something, and the one we have to fix is postulate 6. And if you remember, postulate 2 depended only on postulate 6, so on proposition 2. So we need to fix up those 2 things a little bit. Here are the new versions. So from now on, postulate 6 says, given any 2 distinct non-antipodal points, there exists exactly one line that contains both of them. There's no such thing as antipodal points in Euclidean geometry, taxicab geometry, and hyperbolic geometry. So that non-antipodal is not needed when you're in those geometries, but if you're in spherical geometry, you see that we need that restriction. So that's going to be an addition that's not going to affect us in Euclidean geometry, but it is going to have to take care of a problem that spherical geometry has without that addition. And similarly, proposition 2, which depends on postulate 6, is going to have to be changed a little bit as well. The first part is, if 2 distinct lines intersect, then they intersect in exactly one point if the distance metric is unbounded. Euclidean, taxicab, and hyperbolic geometries have unbounded distance metrics, so there is no largest distance. You can always make something further and further and further away. However, if the distance metric is bounded, spherical geometry, any pair of distinct lines in a plane intersect in a pair of antipodal points. All right? So in Euclidean, taxicab, and hyperbolic geometries, if their 2 lines are distinct and they intersect in exactly one point. And in spherical geometry, no matter what you have, any 2 lines are going to intersect in a pair of antipodal points. All right, next video we'll introduce a little bit about hyperbolic geometry.